Have you ever wondered how an ordinary, pure piece of silicon becomes the complex brain inside every computer and smartphone we use today? Well, it all comes down to a highly orchestrated, microscopic manipulation of quantum physics that's literally happening billions of times a second. Welcome to this explainer on semiconductor physics, taking us all the way from individual electrons to the p-n junction. Let's dive in. Here's our roadmap for today. First, we'll look at current in pure semiconductors. Then, we'll figure out how to hack silicon using doping to create N-type and P-type materials. Third, we'll smash those materials together to explore the p-n junction boundary. And finally, we'll wrap up with the depletion region barrier. All right, starting off with Section 1, current in pure semiconductors. Let's zoom way in on a pure, intrinsic piece of silicon at room temperature. On its own, it actually sits squarely between being a conductor and an insulator. To understand how it conducts anything at all, we really have to look at the atoms themselves. You see, just ambient thermal energy, plain old room temperature, is enough to knock an electron out of its typical orbit in the valence band and push it all the way up into the conduction band. When this electron breaks loose and is suddenly free to conduct current, it leaves behind this crucial vacancy in the crystal structure. We just call this vacancy a hole. Now, because an electron is negatively charged, this empty space effectively acts as a positive charge. So for every single free electron created by this heat energy, one hole is left behind. And that right there is what we call an electron-hole pair. Notice the gray arrows here? Up in the conduction band, those free electrons are just drifting randomly. But down in the valence band, something really interesting happens. A nearby electron can actually pop into an empty hole, which then leaves a brand new hole right behind it. Think of it kind of like an empty seat in a crowded theater. As a person scoots forward into a new seat, the empty space effectively moves backward. So the physical electrons are moving to the right, but the positive charge, the hole itself, effectively moves to the left. We call this hole current. Moving right along to Section 2, doping, N-type and P-type. Here's the thing, pure silicon's natural conductivity is, well, pretty terrible. It's virtually useless for practical electronics. So engineers came up with a brilliant solution called doping. By carefully introducing specific impurity atoms, we can create two completely new extrinsic types of materials. First, if we add pentavalent impurities, which are just atoms with 5 valence electrons, that fifth electron becomes totally free. This gives us N-type material, which is absolutely packed with negative majority carriers. On the flip side, we create P-type semiconductor by adding trivalent impurities that only have 3 valence electrons. When these bond with the silicon, there's a missing electron, which creates a hole. So P-type material ends up being absolutely packed with positive holes as its majority carriers. Check out the visual difference here. On the left, we have an antimony atom, denoted by Sb. It's pentavalent, meaning it brings an extra completely free fifth electron to conduct current. Conversely, on the right, the trivalent boron atom only brings 3 valence electrons, creating a structural gap, or a hole. By doing this, we've successfully engineered the exact charge carriers we need. Pretty amazing, right? Okay, let's look at Section 3, the p-n junction boundary. So what happens when we take a single block of silicon and dope one half to be P-type and the other half to be N-type? Well, the exact instant that boundary is formed, a really rapid sequence kicks off. Step 1. Those free electrons in the N region, which are super crowded and drifting randomly, naturally start to diffuse across the junction right into the P region. Step 2. As soon as they cross over, they find all those abundant holes waiting in the P region and fall right into them, recombining. Step 3, because the N region is losing its negative electrons, it becomes slightly positively charged right at the boundary. And since the P region is gaining electrons, it becomes negatively charged at the boundary. These form what we call ion layers. Finally, step 4. This buildup of opposite charges eventually gets so strong that it literally repels any more electrons from crossing. The diffusion just forcefully halts itself. Which brings us perfectly to Section 4, the depletion region barrier. Let's look at the equilibrium state here. The initial diffusion has already happened. The N region lost electrons, leaving behind a literal wall of positive ions, which you can see in blue with the plus signs. The P region gained electrons, creating a wall of negative ions, shown with the minus signs. Now, this specific middle area is entirely depleted of any free charge carriers. There are no free electrons and no free holes here at all. It's just a rigid, physical barrier of opposite charges. And because we have opposite charges separated by a distance, an electric field is instantly created between them. This electric field acts as a barrier that requires external energy to overcome. If you want to push a new electron through it, you have to spend external energy. And here is a massive takeaway for you. For silicon at room temperature, this barrier potential is universally and predictably equal to exactly 0.7 volts. This is absolutely foundational. Physics naturally gives us this built-in 0.7-volt wall, and it's the exact threshold voltage that engineers have to account for when designing everything from audio amplifiers to CPU logic gates. To put this into a different perspective, take a look at the energy diagram here at equilibrium. Notice how the N region's energy level has actually shifted downward. That gray depletion region literally acts as an invisible energy hill. An electron over in the N region simply does not possess the native energy required to climb that hill and get to the P region on its own. The whole system is just locked in a stable equilibrium. So, by hacking silicon with doping and joining it together, we've manipulated quantum physics to build a microscopic 0.7-volt barrier that stops electrons dead in their tracks. But, this leaves us with a pretty critical question. Sitting at equilibrium, this barrier is a total roadblock. But what exactly happens when we apply an external voltage strong enough to break through that 0.7-volt wall? Well, that is exactly where the true power of semiconductors is unleashed, and what we'll have to explore next.